Let's go ahead and get started. Welcome to Physics 514, General Relativity. I'm in the right place, presumably. Any of you look like you people who want to learn General Relativity. Okay, let me first start handing out some of the syllabi. Here, let me put this back. So let's just start with a little bit of administrative nonsense. So, well, as you may have noticed, it's 8:30 in the morning. I'm not happy. I'm not any happier about that situation than any of you. So one thing I would like to do is discuss possible reschedulings of the class today. Maybe before I do that, I'll just go through and talk a little bit about the class. That way, if any of you suddenly decide that you don't want to take the class, that suddenly makes rescheduling much easier. So let's do that discussion first before we decide anything about scheduling the class. This is an 80-minute class. I think there are 27 lectures throughout the semester. Right now it's scheduled right now, and the place is this place. There's a few. One thing I should mention is I'll probably have to miss a couple lectures in March. I will probably just reschedule them for some other time, so we can burn that bridge when we come to it. Thank you. Let's see. Other information. My name is Alex Maloney. You can call me Alex. My contact information is here. My office hours are here. Our TAs are, one of them is here. The other one has promised to show up sometime during the class today. This is Guillaume. He is one of the TAs. Their contact information is also on the syllabus, as well as their office hours. The TA's primary role in this class is grading and to hold weekly office hours and to answer any questions you might have. Let's see, other important things. So if you are registered for this class, I already have your email address, and I'll use that to send out important communications. I'll send it to your official McGill email address. If you are not registered for this class and you would like to get emails, which probably might be useful because I might have to reschedule classes, then send me an email and I'll add you to the course email list. And just to make sure, did everybody receive an email that I sent last week at some point about rescheduling the class?
No, I didn't.
You didn't. Are you registered for the class?
I'm registered on Forms for Technique, and maybe I'm not registered.
I see. Maybe you weren't registered as of a week or two ago when I got all the names off of Minerva. Would you mind sending me an email just so that I have your email address? Okay, great. My email address is right here. Anyone else not receive? If you didn't receive an email that I sent last week about rescheduling the class, send me an email so that I make sure that I know who you are and what you're doing here. Let's see. I have a course webpage. So I should probably make a comment about my lecturing style. So in the past, the way that I've lectured, as you can probably tell, is using this tablet computer. The advantage of doing this is that I can post the lecture notes and recordings of the lectures online, which is something that a lot of people like. The disadvantage is that it's a little more exciting if I use a blackboard. So I haven't actually decided what I was going to do this semester. One advantage that you guys have is that I've taught this class twice before, and so the recordings and lecture notes from last year's version of the course are already posted on the webpage. So for that reason, recording the lectures and notes is epsilon less important than it was last year. I still might start out using my tablet, but I reserve the right to switch to using the blackboard at some point in the semester if I get sick of using the tablet. Because it is more fun to use the blackboard. And at 8:30 in the morning, we should make things as fun as possible. Do you guys, I guess a lot of you, raise your hand if you were in my quantum class last semester. I think most of you were. Oh, not everyone. Okay. Of the people who, let's put it this way. How many people would prefer Blackboard over tablet? Raise your hand if you prefer Blackboard over tablet. Raise your hand if you prefer tablet over Blackboard. It's pretty even. Okay, we'll see how it goes. Yeah. I've taught this class twice before. I used the tablet both times. Maybe I'll switch to the blackboard at some point just to shake things up. We'll see how it goes. Okay, let's see. Grading, just a general word on grading. This is an advanced class. I think of this as a graduate level class. The grading is correspondingly graduate level, which means that, my goal here is not to give anyone bad grades. If I feel like you understand general relativity to my satisfaction, you will get an A. That said, it is probably not the case that everyone will get an A, but it's also not the case that I'm going to go out of my way to give everyone a C or a D or an F or something like that. So generally speaking, I encourage you not to worry about grades. I think it's a waste of time. Worry about learning general relativity. That's the important thing. Your final grade will be 50% homework, 50% take-home final. The homeworks are extremely important in this class, which is why I've given them half of the weight in the final grade. I think there'll probably be 9, possibly 10 problem sets throughout the semester. These problem sets are non-trivial. I wouldn't necessarily leave them to the night before, or else you might have a very late night. They're important. I encourage you to start working on them early. For those of you who took my quantum class last semester, they're probably not as hard as the ones in the quantum class. But they are non-trivial, and they're very, very important. General relativity is a subject where if you just listen to my lectures, you will really not understand general relativity. You really need to do computations. You really need to, I can lecture, till the end of time about Christoffel symbols and Riemann tensors, but until you freaking calculate 20 of them, you're not really going to understand general relativity deep in your heart. So you really need to do computations. The homeworks are, I think, moderate in length and difficulty. The advantage of having taught this class twice before, from your point of view, is that I've discovered which questions are completely impossible, and I generally don't assign those, but I reserve the right to. Let's see, other comments. I will be handing out solutions for the problem sets. So what that means is that if you hand it, I won't accept late problem sets because the solutions are already out. However, if you have a valid reason for needing to turn in a problem set late, that's okay. So the rule that I will stick to in this class is that if you obtain an extension from me to turn in a problem set late, that's fine, provided you do it before the due date of the problem set, so I know not to hand out solutions. In general, if you have a good reason to ask for an extension on a problem set, that's fine. But you need to get an extension or else I won't accept the late problem set. Let's see. There also will be a take-home final exam. We'll figure out the date for the exam at some point later in the class. It'll probably be either during the last week of lectures or during exam period. It'll be a take-home exam, closed. Open book, open notes. Let's see. Take-home final. You can use your textbook. You can use your notes. You can use your problem sets. You cannot use each other. You cannot use the internet. You cannot use other textbooks. You cannot use papers. You cannot use Ouija boards. You cannot use psychic power. Well, you can use psychic power if you want. Okay, good. Let me say a little bit about the prerequisites for this course. So I think in general, anyone who is in the final year of the undergraduate program here is just fine. The mathematics prerequisites are not particularly advanced, but deep, if you get what I mean. You need to know multivariable calculus backwards and forwards. You need to know linear algebra backwards and forwards. Those are the two most important requirements for the class, probably. You need to know some differential equations to the point where you're not scared of some horrifyingly long differential equation that you might encounter. You need to know special relativity, of course. I mean, this is something that always is a slightly confusing issue because no one ever actually takes a course just on special relativity. It's always fit into some weird little 2-week session in some other course. So maybe I can take a poll of the audience. How many of you have seen special relativity at least once? Good. Okay. If you have not seen special relativity, you should probably come talk to me because that might make your life difficult. This class, I will review special relativity this lecture and next lecture. It will be a advanced review of special relativity, which will probably be largely new even to many of those of you who have seen special relativity. So if you have not seen special relativity, then you should probably come talk to me and I can tell you, we can discuss the situation, I can tell you what you might need to read to get up to speed. How many of you have seen special relativity like twice? Okay. So what class did most of you see special relativity in? Was it some stupid U0 class? Yeah, okay. So you guys, how many of you know what a Lorentz transformation is? Raise your hand if you know what a Lorentz transformation is. Raise your hand if you know what the line element of, okay. Raise your hand if you've heard if you know what Minkowski space is. Okay. Okay. That's useful for me to know. How many of you saw special relativity in your electromagnetism class? Okay. Good. So, okay. The other main requirement for this class is a pretty solid background in undergraduate mechanics, sort of at the level of Hand and Finch or Marion and Thornton or something like that. How many of you have taken sort of an advanced undergraduate mechanics class and feel comfortable with actions, Lagrangians, all that stuff? Okay. If you have not taken such a class, you may have a little bit of catch-up to do. General relativity is a fairly self-contained subject, so if you know enough math, you can get away with a lot in learning general relativity. However, in a lot of what we do, it's not that the subject of general relativity requires a lot of physics prerequisites in and of itself, but it is the case that there's a certain mathematics and physics sophistication that will be expected in this course. So if you have not taken, the analog of physics 451 or whatever, 351 I think they now call it, you may have a little bit of catch-up to do in this class. For example, I will expect you to understand actions, how to obtain equations of motions by varying actions, Euler-Lagrange equations, stuff like that. Okay. And of course, I will assume that you have seen some electromagnetism. Again, this is not a class in electromagnetism, so it's fairly self-contained. But the closest analog to general relativity that you have seen in your lives is electromagnetism and is Maxwell's equation. So frequently in this class, I will refer to electromagnetism as a way of building intuition about general relativity. So how many of you have taken 2 semesters of undergraduate electromagnetism? So presumably everyone in their 3rd year. How many of you have only taken 1 semester? So if they're, okay. Okay. Just for my edification, how many of you are U3 honors students? Okay. How many of you are graduate students? Okay. What fields are you guys graduate students in? What's that? HEP experiment, yeah. HEP theory, right. Astro, good. Condensed matter. Okay. General relativity is useful for all of those things, even condensed matter, I think, depending on how you think about it. Yeah. Okay, that's good. Let's see. What else do we have to say? Oh yeah. How many of you are U2s? Okay. Yeah. I don't recommend against U2s taking this class, but I think that you have a little bit of catch-up to do to succeed in this class. So if you're concerned, I recommend you come talk to me, and we can figure out exactly how well that we can figure out exactly the situation. How many of you are not in the honors program here? Okay. Again, this class is, I think of this as a graduate level class. I teach this class at the level that I took it when I was a graduate student. And so I think that there's nothing, you guys have, those of you who are regular physics majors instead of honors have the background to see this class, but there might be little pieces of things here and there that you might have to do a little bit of extra work for. But I think that in general that should be a minor, not a major concern. Let's see. The textbook, actually, one of the nice things about the class is that the textbook is really excellent, I think. It is this book by Sean Carroll. I actually ordered it at Paragraph Books, not at the McGill bookstore, because Paragraph Books is much more competent than the McGill bookstore. It's quite good. In general, I think that the explanations in the text are very good. The problems are not great. So for that reason, I write a lot of my own problems. I don't completely like the way that the subject is organized in the textbook. Question.
What about the stuff he has online?
Does he? Oh, yeah, right. There's something on the archive.
Yeah.
So Carroll, before writing the textbook, wrote like a preliminary version of the textbook, which he posted online. I would recommend getting the textbook because there's about twice as much stuff in the textbook as there is in his notes online. These are posted on the archive if you want to take a look. I think the textbook, I would recommend the textbook over his notes online. Also, I will assign some problems from the textbook for the problem sets. Some of them are pretty good. Some of them are not so good. But I would recommend getting the textbook. It's good. It's a good textbook. People like it. I think the explanations are very good. I don't completely like the way that he organizes the subject, so I don't stick incredibly closely with his structure, but I think his explanations are good. And I think that you'll enjoy it. Other books you might want to take a look at. There's a book by Schutz, this little green book on general relativity. I think that's a wonderful book. It's very, very readable. You could sit and in a weekend read the whole thing and learn a lot. It's taught at it's a slightly lower level than I think is appropriate for this course. So I don't use it as a textbook, but it's a great book. I recommend that you take a look at it, especially if you're looking for an alternate point of view. The other book I really recommend taking a look at is Einstein's book. It's just 4 lectures. It's beautiful. It is not, it's short. It's like 100 pages. You can read it in a weekend. It's a very philosophical, there's lots of meaty kind of philosophy. And there's nothing better than learning physics from the person who invented that subject, right? So you should read Dirac's book on quantum mechanics. You should read Coleman's book on field theory. You should read Einstein's book on relativity, right? These are just things you should do as a physicist. So, I think it may not, I don't think it will help you too much as far as, learning exactly how to think about the Riemann tensor, for example. But it's a beautiful book, and I really recommend it. Other books, Hartle has a book, it's an undergraduate book on general relativity. It is at a considerably lower level than this course. I don't know it particularly well, but people love it. So I think it's quite well written. He's sort of a real master of the subject. So you might want to take a look at that. Dinverno's book is essentially identical to Carroll's book. The explanations aren't quite as nice, but it's got like pictures in it, which are nice. So that's a sort of alternative to the main text. Weinberg's book was the standard book on general relativity for a very long time. It's sort of unique in that it treats general relativity in a non-geometric point of view. This is somewhat old-fashioned. It's not really the preferred pedagogical style nowadays. But if you want an alternative perspective on general relativity, I do recommend you look at Weinberg's book. It's quite well written. He's a very, very good writer. It's very thorough. The section on cosmology, I think, is especially good, even though it's about 25 years out of date. But, you know, people understood a couple of things 25 years ago which are worth knowing. Let's see. Misner, Thorne, and Wheeler is like this gigantic book. It's like 2,000 pages long or something ridiculous. I hate it. Some people love it. It's got a lot of interesting topics that you won't see anywhere else. Wald's book is the standard reference book on the subject. It's the book that everyone has on their bookshelf, but never actually reads. It's where you go to learn some special topic that you never actually learned in your general relativity class because it's too advanced. I'm not a huge fan. I think it's very technical, but it's a useful place to look for advanced topics if you find that Carroll is not advanced enough for your tastes. The other book is the one by Hawking and Ellis. Again, there's a lot of good stuff in there that you won't see anywhere else. It's very mathematical. It starts on page 1 with the definition of a Hausdorff manifold, right? I mean, roughly speaking, your rule as a physicist is that once someone says the word Hausdorff manifold, your brain should turn off. So I think it's a little too, it's way too mathematical for a textbook. There's a lot of good stuff there that you won't find anywhere else. Okay. The nice thing about general relativity is that because it's such a sort of elegant and self-contained subject, there are a lot of good textbooks on the subject. So you won't find yourself lacking resources should you need extra places to look. I guess in the past I've put these books all on reserve at the library, but then at the end of the semester I checked with the library and not a single person had ever come and taken a look at them. So I didn't bother to do that this semester. But I think the library has all of these books, probably multiple copies. Okay, finally let me just say a little bit about the outline of this course. Let me start by saying that I absolutely love teaching this class. General relativity is one of the most beautiful subjects in theoretical physics. This is absolutely my favorite class to teach. It's a truly lovely subject. It's also quite self-contained. So unlike other classes, we're really going to start at the beginning and understand the entire structure of general relativity from the ground up. So for that reason also, it's a very enjoyable class to teach because you will learn everything you need to know about the basics of general relativity in this class from A to Z. Why? Not Z. So the way that I'm going to structure this class is the follows. So the first 2 lectures, this lecture and next lecture, will be essentially what I consider an introduction. I'll start with a very bare-bones 15-minute sketch of the ideas of general relativity before talking about special relativity for maybe a lecture and a half. Again, this discussion of special relativity will probably be, in a way, it'll be in a style in a way that might be new to you, even if you've taken a course where they covered special relativity. And then then roughly speaking, after that, the class will be divided into 3 parts. So for the first third of the class, we'll essentially be doing mathematics. Now, general relativity is a beautiful, self-contained subject, but it is a mathematical subject. And a lot of the mathematics that you'll learn in the first third of this class is reasonably advanced mathematics, which I think none of you have probably seen before. So there's a sense in which the first third of this class is going to be the most difficult, probably for a lot of you. The math that you learn is differential geometry. Now, there are classes in the math department here on differential geometry. But by and large, the differential geometry that we see here is the sort of stuff that you would see in a graduate level differential geometry class, rather than an undergraduate differential geometry class. Now, of course, you're not math graduate students, so this won't be taught at the level that you would, it won't be taught in the style and at the level of abstraction that you would see it in this class, but that's the material that you're going to see. It's sort of graduate level differential geometry. That said, it's not particularly difficult. It just takes some time getting used to. So I think you should be prepared for the fact that the first third of this class might be the toughest going in terms of the rate at which you're expected to absorb new ideas in this class. So we'll learn about manifolds, differential forms. How many of you know what a differential form is? That's a shame. That's a shame. That is a real. Okay, you're gonna learn what a differential form is. Yeah, it's a shame they don't teach differential forms. Okay. Well, I will rectify that situation. How many of you know? No, none of you know that. Okay, never mind. Then we're going to see covariant derivatives, curvature, all that good stuff. That'll be a pretty, more mathematical digression. The next third of this class will be spent covering what I think is sort of the core of this class. We'll see Einstein's equations. We'll discuss the basic formulation of general relativity and the basic solution of general relativity, which is the Schwarzschild solution, which describes the curvature of space-time around a spherical object. And then we'll use that to discuss the three classic experimental tests of general relativity: gravitational redshift, precession of orbits, and gravitational lensing. So these are the three famous experimental tests of general relativity that were used to successfully test the predictions of Einstein in the first half of the 20th century. And then in the last third of the class, we'll spend some time doing some special topics which are relevant for general relativity in the second half of the 20th century and the first decade of the 21st century. So we'll spend about a week on the study of black holes, a week on cosmology, maybe a little more on cosmology, and a week on gravity waves. So those, I think, are the three most important special topics in the subject of general relativity, both for experimental relevance. I mean, astrophysicists see black holes. They measure aspects of the cosmology of the early universe. And indeed, we're spending millions and millions of dollars building gravity wave detectors. So that's a very interesting subject. And then, if we have time, we'll spend a little bit of time doing some advanced topics. I have a lecture written on Hawking radiation. We could also do some more advanced stuff on black holes, or talk about inflation. We'll just have to see how much time we have at the end of this course. Generally speaking, every time I teach a class, I go about 10% faster than I did the year before. Last year, so based on that algorithm, I might have an extra lecture at the end of class, but I'll try not to go too quickly. The other thing that I should comment, I really want to encourage all of you to interrupt me, to ask questions. I will try and stop as frequently as possible to encourage you to ask questions, but really, this only works if you interrupt me and ask me to clarify if things are unclear. Are there any questions about the structure of this course? Any administrative questions? Have I left anything out? Yes, question. Okay, yes, that is an excellent question. Okay, now let me just say, you will probably have a much better experience in this class if I am not forced to lecture at 8:30 in the morning. I have given 8:30 classes before. My lectures are brilliant no matter when I give them, but they are even more brilliant when I've had a decent night's sleep. So I would prefer to reschedule the class. I also know of at least one person who I don't know where. Okay, I know there was at least one person who emailed me and said that they had a conflict with this time. Apparently one of the math class, you.
I don't have anyone.
You don't? Okay, that's unfortunate. You don't have a conflict anymore. So is there anyone who has a course conflict at this time? That would be lovely, because that would give me even more. You have a course conflict. Oh, yeah. Unfortunate, as sympathetic as I am to that. Okay. Okay. Now, I did send out in an email a little poll about the preferred times for this class. Yes.
I can know someone might have a course, but I'm not sure.
Okay.
Algebra 4 or something.
Algebra 4?
Well, it's not me, so I'm not sure.
Yeah. Do you know who the person is?
Yeah.
What is the person?
Chinese person. I'm going to try to.
Oh, okay.
Young.
I don't know. Is that because there was an algebra course that was conflicting, which apparently is now not.
Algebra 4 conflict.
But you're not taking it. Okay. Oh, that's Okay, so Algebra 4 does conflict, so there is one possible course conflict. You sure you don't want to register for Algebra 4? I'm joking. Okay. Yeah. So I did send out this online poll, which most but not all of you completed. Now, unfortunately, there was no single time that worked for absolutely everybody. It appeared like the best time. Okay, The best time appeared to be Thursday afternoons, but there were a few people who couldn't make it Thursday afternoons. So let's see if we can understand whether that can be worked around. So, who are the people who it looked like there were 3 people who could not make it. So one of the proposals was Tuesday, Thursday, 4 to 5:30. And another proposal would be Tuesday, Thursday, 5 to 6:30, or possibly 5:30 to 7. I'd rather not go past 7. So who had a conflict? There were a couple people who had conflicts. Raise your hands. There should be 3 of you. You had a conflict. Is it a real conflict?
Yeah, it's a lab class, which is a required class for me. It's going to class.
Okay. Which lab class is this? Because I know that there's one. Is this the class that meets once a week? This is Measurements 5. Okay.
Mm-hmm. I might have a conflict as well.
You might have a conflict as well. Okay.
I have a conflict in the later one.
You have a conflict in the later one. Okay. Because I know that one of the lab classes is officially scheduled for like a Tuesday or Thursday afternoon, but in fact you can do it whenever you want during the week. Does anyone know if the Measurements Lab is one such class?
Yeah, okay.
Yeah. Yeah, I would rather not make people skip classes. Yeah. Did you have... What's that? Yeah. How many people took the Measurements? Most of you probably took the Measurements Lab class. No one took the Measurements Lab? Isn't this a required class? Not for honors. Okay. So, raise your hand. Okay, so you have a possible conflict. Who else? You had a conflict? Possible conflict.
I might have a conflict. I'm not sure about my business.
Okay. Did anyone else have a conflict? You had a conflict. With another course?
No, with varsity.
Boy. Physicists, athletic team. Okay. I'm sorry, joking. Okay. No, I'm very proud of you. Okay. Sorry. I'm sorry. It's too early in the morning. Okay. Another possible time was Tuesday, Thursday, 11:30 to 1. But I did notice there were 4 people who couldn't. Raise your hand if you couldn't make Tuesday, Thursday, 11:30 to 1. You couldn't make it also. You can't make it. Are these course conflicts or these seminars? Yeah. When is the course? 11 to 12?
11 to 12:30.
11 to 12:30. Huh. I didn't know that there was a course that was a time slot. We could try Monday, Wednesday at 4 to 5:30. How many people had a conflict then? You had a conflict with a course?
Religious studies course.
Okay. You had a conflict?
Yeah, with the modern physics.
Okay. Oh, it's the modern physics lab, I think, is the one that... It's the same one that you also have a religious studies class. Okay. Far be it from me to try and impugn on your religious... This is how you get in trouble. Jeez. Okay. When is the class that you have a conflict? What time is it?
4 to 5:30.
It's 4 to 5:30. What about 5:30 to 7 on Monday?
It's too late.
It's too late. People can't do classes at that time. You would rather have an 8:30 in the morning class. You would rather make me get up 27 times. I suppose that's fair. I am usually already awake. If you didn't see my desktop background, if you saw my desktop background, you'll understand the reason why I'm usually already awake. But not in okay.
I really feel like if everyone is free now, 8:30 to 10, and some people have course conflicts at all the other possible times, I don't feel like I can reschedule the class. Anyone have any creative suggestions?
We can wait and see till people drop out. Can we
Yeah.
put this up to like a week? Or?
Let's do this. Let's reopen this discussion in a week. Does that sound reasonable? Because at that point, anyone, some of these lab classes are scheduled for particular times, but don't actually happen at those times. You just go whenever you want. Some, things get rescheduled, things get shuffled around. Let's reopen this question in a week. And in the meantime, I'll just have some coffee. Yeah. I suppose you guys don't want to come in on Saturdays. No. No, I would get in trouble if I had to come in every Saturday. Okay. All right. We'll reopen this discussion in a week. Okay, good. Any other questions of an administrative nature? No other questions? Administrative. Everyone is completely delighted with all such things. Yes, go ahead.
What topics you suggest we catch up on?
For the U2s, you're presumably taking the undergraduate mechanics class right now. So that's probably okay. It's more as we discover topics that you are uncomfortable with, you will have to do a little extra reading on those topics. For example, let me ask, how many of you have seen the electromagnetic field strength tensor? Okay. For example, you will need to understand what the electromagnetic field strength tensor is. You probably only see that in your EM waves class. Is that correct? How many of you have seen Einstein's summation notation? How many of you feel completely comfortable with Einstein's summation notation? Okay. So you will probably need to spend a little epsilon extra time becoming comfortable with Einstein's summation notation. Einstein's summation notation is the sign of a sophisticated mind. So everyone should become comfortable with Einstein's summation notation. What other stuff? Those are the two, and you also might need to brush up on special relativity. That might be true of everyone in this class. The first chapter of Carroll does a bit of special relativity. I'm not a huge fan of the way that he presents it. I think the Feynman lectures actually have, the first volume of the Feynman lectures, a very lovely discussion of special relativity. So that's a good place to look. Also, your E&M textbooks probably have a very nice discussion of special relativity. I know the Griffiths E&M textbook near the end has a very nice special relativity discussion. That's actually a pretty nice place to look. I don't know if you guys, do you guys use that as your textbook for E&M? Yeah. So those would be two things to look at for special relativity. Okay, so that's a good question. If you have any of you who are worried about possible prerequisites, you can come and talk to me. I mean, generally speaking, if you feel like you can hack it in the class, you should take the class. I mean, but you should be prepared that you might have to put in 20% more work than other people in the class. But it's okay. It's work learning physics. It's not work. Okay. Any other questions? Okay. Let's go ahead and get started and do some physics then. General relativity is probably one of the two pinnacles of theoretical physics. And I think that I am very excited to teach this class. You all should be very excited to take this class. It's a truly beautiful subject. And it's one of those rare times in your careers as physicists when you will have your viewpoint on physics fundamentally shifted. Most of what we do when we study physics is a story of rather incremental progress, successive reformulations of theories in gradual ways. But I think it's fair to say that general relativity represents a rather profound shift in the way that you think about very basic notions in physics: space, time, gravity, curvature, these sorts of things. I think the only comparable event in your lives as physicists is the first time you see quantum mechanics. That perhaps is an even more radical and important shift in your point of view. And I would say general relativity probably it comes in a close second to that change in your point of view. So before diving into any mathematical details, differential geometry, special relativity, all that stuff, what I would like to do is begin with a very general introduction, just to sort of whet your appetites and to give you a flavor for what it is we are going to be doing for the first half of this course when we introduce basic notions of geometry and use them to formulate the equations of motions of general relativity. So, what is general relativity? General relativity is the modern theory of classical gravity. Classical, because in this class h bar will be set equal to 0 for essentially the entire class. So no quantum effects will be considered or discussed in this class, in part because we don't know what the correct theory of quantum gravity is. So this is a subject where we are really pushing up against the forefronts of knowledge. Throughout your lives as physicists, you've mostly studied things that were pretty well understood in the 19th century or the first half of the 20th century. By the end of this class, we will be pushing up against things that are not terribly well understood in our study of black holes, our study of cosmology, and so forth. So this is really a class on modern physics. General relativity is also the theory of gravity. Now, you have seen gravity before in your studies of Newtonian physics. And so what I would like to do now is just tell you in rough terms how it is that general relativity alters our point of view about gravity from that which you encountered when you studied Newtonian physics. So, what is the basic idea? So gravity is a force. It's one of the four fundamental forces of nature. And one of the things that you have learned in your lives as physicists is that forces are described by fields. So you have previously encountered two examples of forces which are described by fields. So in your study of Newtonian gravity, you encountered the Newtonian gravitational field, phi. And in your studies of electromagnetism, you encountered the electromagnetic fields, E and B. And general relativity can be thought of as a different sort of theory of fields, which describes gravity. So before describing what general relativity is, I should tell you what the ingredients are which go into a description of the forces of nature involving fields. So a theory of fields typically has two distinct parts. So there are two ingredients which are necessary in order to formulate a theory of forces involving fields. So the first ingredient is the equation of motion. So what is the equation of motion? The equation of motion is a differential equation, usually a second-order differential equation, which allows you to determine the field in terms of the sources. And this equation of motion for a field usually goes under the creative name of the field equation. For example, the Newtonian gravitational field satisfies Laplace's equation. So grad squared phi is equal to 0 in the absence of sources, or if you have sources, it's proportional to the mass density present. So rho here will be the mass density, along with a constant of proportionality, which is Newton's constant, with some conventional factors of 4 pi. The second example of a field equation is something that you're probably even more familiar with, which is Maxwell's equation. So Maxwell's equation is a set of differential equations which determine the electric and magnetic fields in terms of the charge and current densities. And they're first-order equations for the fields E and B, but if you write things in terms of the scalar potential V and the vector potential A, they're second-order differential equations. And in general, all of the field equations of physics turn out to be second-order differential equations. So the field equation is the first part of a field theory, which allows you to determine what the electromagnetic or gravitational field is in terms of the sources. And then, of course, you need to describe how it is that this field affects physics. So what we need is an equation which determines the motion of objects in the presence of a field, which is usually referred to as the force law. So the force law is an equation which determines the motion of objects in the presence of a field. So, for example, in the case of Newtonian gravity, the force on a particle in the presence of a gravitational field, well, that force is the mass times the acceleration of the particle, which is then, in the presence of a gravitational field, just equal to the mass times the gradient of the Newtonian potential. So this is the usual force law, the 1 over r squared force law for Newtonian gravity. Or, in the case of electromagnetism, the force on a particle due to the presence of an electromagnetic field is given by the Lorentz force law. So the force is proportional to the charge of the particle times the electric field, plus, if the particle has some velocity, v cross v. So a field theory has two parts. The first is an equation of motion which allows you to determine the field in terms of some sources by solving a differential equation. And the second is a force law which allows you to decide how it is the presence of some field will affect the physical motion of objects. Any questions on that? So far, I haven't told you anything that you don't know, presumably. So, let me start now to tell you things that you perhaps don't know. Or if you know them, you probably shouldn't be taking this course. So, how does this differ in the case of general relativity? So far, we have taken the fields to be functions of space-time. So they're functions of t and x. Sorry, no vector symbol on the t. So the gravitational potential phi depends on what time it is and where we're sitting in space. Likewise, the electromagnetic field will also depend on the time and our spatial position. And the force law tells us how motion will differ
from that of a straight line in the presence of a field. So, for example, if there's no gravitational potential or no electric and magnetic field, then we just have A is equal to 0, so that the motion will be in a straight line. However, if we have some non-zero gravitational or electromagnetic field, then motions will deviate from straight lines. So this is the basic picture that we all keep in our heads when we think about force laws in classical physics. But in general relativity, we need to rethink that basic picture. So in general relativity, gravity is not due to a field which is a function of space-time points, but it's rather due to a feature of space-time itself. So, in your previous studies of classical field theory, space-time has just been a fixed object, a set of points and times that has not had any particular role to play except as the background on which the interesting objects, the gravitational potential and the electromagnetic field, play their game. In general relativity, however, we interpret the existence of gravity not to a field which lives in a fixed space-time, but rather to a feature of space-time itself. And so we replace the notion of the gravitational potential by a new quantity, which could be thought of as a field, but is perhaps better thought of as a feature of space-time itself, which is known as the metric tensor. So rather than being a single quantity phi, which is a function of t and x, it is now a collection of 16 functions of t and x called g mu nu, where mu and nu are indices that label these different 16 quantities. And this metric will describe the curvature of space. And there is a field equation, just like for the other field theories of classical physics. And the field equation describes, or the field equation allows you to determine the curvature of space in terms of whatever sources are present. So it tells you that if you have matter present, then space-time will curve in response to that matter. So just like the equation of Newtonian gravity that I wrote down for you earlier, this equation is a second-order differential equation. It is a second-order differential equation for the metric tensor, g mu nu. Let me write it down for you. I don't particularly expect you to understand that equation, but you should compare it in your mind to the equation that we wrote down earlier for the Newtonian gravitational potential, where the left-hand side of this equation is some quantity which is second order in derivatives of the metric, which describes how space-time curves, and the right-hand side of this equation has a prefactor involving Newton's constant, which is the constant that parameterizes the strength of gravity, times some quantity here, which tells you about the sources, the matter that's present. Now, in relativity, of course, you know that mass and energy are the same thing, So this quantity that I've called T mu nu, that sits on the right-hand side of the equation of motion, will tell you not just about the amount of matter that's present, the amount of mass that's present, but also the amount of energy that's present, and also the amount of momentum that's present. And so this quantity T mu nu is known as the stress tensor, and it's the thing that acts as a source for Einstein's equation. And this field equation is known as Einstein's equation. And it is the basic equation in general relativity which allows you to determine the curvature of space-time in response to any mass or energy that is present. Now, a field theory has two components. In addition to a field equation, there is also a force law. And if anything, the force law is even deeper and more profound than Einstein's equation. So the force law is what is known as the geodesic equation. Let me again write it down for you. Again, I don't expect you to understand all of the symbols that I have written down. I'm just writing it down to whet your appetites. And this geodesic equation describes how objects move when space-time is curved. And the important point, the essential point about general relativity is that this force law can be thought of as very different in character from the force laws of Newtonian gravity or electromagnetism. So in particular, in electromagnetism, for example, the Lorentz force law tells you how the motion of objects deviates from straight lines in the presence of an electromagnetic field. In general relativity, however, the force law tells you not that objects deviate from straight lines, but only that they travel on lines that are as straight as possible in a curved spacetime. So the geodesic equation says that objects travel in lines which are as straight as possible in curved spacetime. Such lines which are as straight as possible are known as geodesics, hence the name geodesic equation. So intuitively, the way that you should think of it is the following. In the absence of gravity, space-time is completely flat. You could think of it as a flat piece of paper. And a straight line on a flat piece of paper is just a straight line. It's what you always think of as a straight line. And in the absence of gravity, nothing special is happening, and a straight line is just your usual notion of a straight line. However, if you have some matter present, if you have some curvature present, then space-time is curved. So the simplest curved geometry that you could think of might be a sphere. And indeed, you know that there's no such thing as a perfectly straight line on a sphere. But there are such things as lines which are as straight as possible, given the fact that the sphere itself is curved. So such lines you have surely encountered in your lives. They are known as great circles or arcs of great circles. And the geodesic equation, the force law of general relativity, just says that objects move on lines which are as straight as possible on this curved spacetime. And the truly remarkable thing about general relativity is that this notion that particles travel on lines which are as straight as possible but in a curved background completely characterizes classical gravity. So the fact that one can describe the motion of objects in terms of the curvature of space-time and in terms of the motion of on lines which are as straight as possible in a curved background is the truly remarkable and miraculous thing about gravity. And it's what allows the beautiful geometric formulation which we are going to discuss in this class. So this then, I think, should give you at least a little bit of motivation and a little bit of an idea of where we're going to be going for the next 3 or 4 weeks. So for the next 3 weeks or so, our job is primarily to make sense of all of the symbols that have appeared in this equation. And then we'll understand and study Einstein's equation before, in the last third of this class, understanding its applications to various special cases. So what I would now like to do is go ahead and dive into a more detailed discussion of exactly what we mean when we say space-time, and in particular into a discussion, a review of some aspects of special relativity. Before I do so, let me pause and see if there are any questions. No questions? Everything is crystal clear? It's just too early in the morning for questions. I'm not going on until someone asks a question. Okay. What is love? Okay. Let's move on. Yes, there's a question.
How do you know that there's always a unique path of traveling from space-time in an extreme way?
Of course. That's an excellent question. So, the question was, how do you know that there's always a unique path to travel? The answer is that there is not always a unique path to travel. So just as in classical mechanics, the path that we take through space-time depends on initial data, such as my initial position and velocity. Because the equations of motion are second-order differential equations, I require 2 pieces of initial data to uniquely specify a trajectory. Those pieces of initial data could be taken to be my initial position and velocity. And as we will see, precisely the same thing is true in general relativity. So for example, if you look at this geodesic equation, you can see that there's a symbol here with 2 dots. That means it's a second-order differential equation. So essentially the same idea holds.
Could you, for example, imagine something, just there's a splitting and both dots could be taken, and there's nothing that can tell you which way you would be going?
No. In a classical theory, such things don't happen. Now, in quantum theory, of course, as you know, there is a sense in which one can take multiple paths at the same time, but that, I think, is beyond the scope of what we'll study in this class. There is a sense in which what you're saying is correct in the following way. So, if I choose to ask for a geodesic which connects 2 given points in space-time, then in flat space, there's a unique geodesic. So if I have one point here and another point here, there's a unique straight line which connects the 2. But on a curved geometry, that's no longer necessarily the case. So for example, if I have the north pole of the sphere and a point on the equator of the sphere, there are in fact 2 geodesics, 2 straight lines which connect those points. One of which is the short one, and the other of which is the long one, which goes all the way around the backside of the sphere. So there is, in that sense, a notion that geodesics are not quite as unique in general relativity as they are in special relativity. So that's just a feature of life in curved space. Yes, additional question. For the North Pole and the South Pole, of course, there are an infinite number of geodesics that connect them. Absolutely correct. Well, what are these geodesics? So if I am at the South Pole down here, then I have my initial position is the South Pole, and I have an initial velocity. If I'm
or maybe I don't, but if I do have an initial velocity, then that will tell me which geodesic I take to the North Pole. So, for example, what is not true is that there's a unique shortest geodesic between the North Pole and the South Pole of the sphere. Between the North Pole and the equator, say, there is a unique shortest geodesic. It's the one that I've drawn here. But between the North Pole and the South Pole, there is no unique shortest geodesic. That's life. That's life in curved spacetime. Good. Other questions? Okay. Let's continue. So, what is spacetime? So, space-time is something that in your previous physics classes you may not have spent all that much time talking about or thinking about in any depth. But I think it's useful for me to tell you exactly what it is I mean when I say space-time. So, loosely thinking, we should think of space-time is the set of all possible times and positions. So here I am using a Cartesian coordinate system where x vector just stands for x1, x2, and x3, the set of three quantities which label a point in space. And a point in space-time is often referred to as an event. We call it an event to distinguish it just from a point, because usually we often think of a point as just a set of x1, x2, and x3 that label the spatial position. But in space-time, we also need to specify the time at which something occurs. And so we usually refer to it as an event rather than a point. Often, however, I will just be sloppy and refer to events in space-time just as points. So I'll use the phrase event and point interchangeably. So what is space-time then? Space-time is a set of points or a set of events which can be labeled or parameterized by a coordinate system such as Cartesian coordinates or polar coordinates in a smooth way. So what exactly I mean by smooth way and what exactly I mean by this notion is something that we will make a bit more precise later. But you should think of space-time as just a set of all possible events, all possible times and positions, and the points in space-time are labeled by coordinate systems. So, for example, if we were to use a Cartesian coordinate system, the points in space-time would be labeled by four numbers, t, x1, x2, and x3. Whereas if we were to use a polar coordinate system, the points in space-time would be labeled by a different set of four quantities, t, r, theta, and phi, where theta and phi are two spherical coordinates. And the basic principle, which underlies everything that we will discuss in this class, is what is known as the principle of general covariance. So the principle of general covariance is simply the statement that physics should be independent of the choice of coordinate system that one uses to describe points in space-time. So, for example, whether I choose to describe physics in special relativity using Cartesian coordinates or using polar coordinates should not have any influence on the outcome of physical experiments, should not have any influence on the actual physics. And
although this sounds like a rather trivial statement, after all, a coordinate system is just something that we introduce for our convenience in order to make sense of physics in an analytic manner. In fact, this is a very deep statement, and it will be our guiding principle throughout the first half of this course as we try and understand how to write down equations of motion and study physics in curved space. So in fact, the principle of general covariance is a very deep one and is possibly the most important concept in this course, and certainly the motivating concept for the first half of this course. Any questions on that? If that sounds all rather loosey-goosey and philosophical, don't worry. It will become much less loosey-goosey later on in this course. Okay, so let's now talk about some of the implications of this notion of general covariance. So let's imagine that we're just thinking about Newtonian physics. In a Cartesian coordinate system. So that means that we could imagine two events, one of which happens at time t1 and position x1, as well as time t2 and position x2. We could then ask, given these two events, what are the interesting physical quantities that I might consider when formulating my laws of physics? Now, the numerical value of T1, for example, is not something that independently has any physical meaning. T1 is just the label that I use to measure a particular value of time in some coordinate system. It could be the time as measured from midnight last night, or the time as measured from midnight tomorrow, and the numerical value of T1 won't have any physical significance. Something that will, however, have physical significance would be the difference in time between T2 and T1, or likewise the difference in position, delta x, between the 2 points. So the distance between the 2 points, delta x, will be given by the Pythagorean formula. So it's x2 minus x1 dotted into itself, and then we take the square root. So whereas in the four quantities T1, x1, x2, and x3 don't make independent sense in Newtonian physics, the two quantities, delta t and delta x, make sense independently in Newtonian physics. If I were to try and formulate a law of physics in Newtonian physics, I would write it down in terms of delta t and delta x. I might say that the relative position between the two of them would change as a function of time in some way, according to some force law. However, in special relativity, delta t and delta x do not make sense independently. Instead, these notions, so in particular, for example, delta t will correspond to the notion of the time separation between two events, and delta x will correspond to the notion of the spatial separation between two events. But in special relativity, as you know, there is no independent notion of the time separation between two events, or the spatial separation between two events. For example, as you well know, we have time dilation as well as length contraction in special relativity, both of which mean that the two notions, that of time separation and of spatial separation, depend on which reference frame we use to define these notions. So, for example, if I consider two reference frames which are moving at constant velocity with respect to one another, then the relative time as measured by an observer in one of those reference frames between two events would change depending on which reference frame I'm using. That's just another way of saying that in special relativity, delta t and delta x are not quantities which can be used to define laws of physics in a way which is consistent with the principle of general covariance. There is a change of coordinates, namely one which takes me from between two reference frames that are moving at constant velocity with respect to one another, which mixes delta t and delta x. Such a change of coordinates is known as a boost, and it's something that you presumably encountered in your classes on special relativity. In special relativity, however, there is one independent notion which does make sense in and of itself. And that is the notion of the invariant interval. So in special relativity, there is one notion which does make sense independently, and that is the notion of the invariant interval, usually referred to as delta S, which is given by the formula delta S squared is minus delta t squared plus delta x squared, with a constant of proportionality in front of delta t squared to make the dimensional analysis work out. That constant of proportionality, c, has dimensions of length over time, otherwise known as dimensions of velocity, and of course is nothing more or less than the speed of light. So, raise your hand. How many of you have seen the notion of an invariant interval in your special relativity class? Good. Okay. It's a notion that we will spend perhaps the next lecture reviewing and understanding in greater detail. However, the first thing I should do is remind you all that I'm an extremely lazy person. For that reason, I will use units where c is equal to 1, and the invariant interval is just written as minus delta t squared plus delta x squared. So, in particular, I will use units where c, instead of being equal to whatever it is, 3 times 10 to the some number, 8, I guess, meters per second, instead, I will just use units where c is equal to 1. So, for example, that means I will use as my measure of distance, the light seconds, so that the speed of light is 1 light second per second. I don't know how long a light second is. A few 100,000 miles. Probably slightly more kilometers. Okay, it's 9:55, which is the end of the lecture. So let me just end with one final statement, which we will return to at the beginning of class next time. So this is a claim that I will explore in class next time, which is the following. All of special relativity is just the following statement. It's just a statement that for two events, say t1 x1 and t2 x2, the time measured by an observer moving at constant velocity between those 2 points is given by the formula. So it's equal to delta tau, which is given by the formula delta tau squared is minus delta s squared. So this invariant interval that we have defined has a simple physical interpretation. It is just the proper time measured by an observer who is moving at constant velocity between these 2 events. In other words, it's the amount of time that's elapsed on a clock which is carried by this observer moving at constant velocity. And everything that you learned in your course on special relativity, length contraction, time dilation, all of that is all just this one statement. And so the fact that everything you know about special relativity is just this one statement is something that might not be immediately apparent to you, but it's something that we'll see next class. So maybe I'll end here unless there are any questions. All right, see you on Monday, bright and early, 8:30 a.m.